Hello, this is a warning to tell you that in what follows I systematically mispronounce the word decay. I pronounce it incorrectly as decay, as many people do, and I'm very sorry about that. So this is just a notice for you to understand that it should be pronounced correctly as decay. Look here.
Decay.
Decay.
Okay, so you heard both British and American pronunciation. So try to pronounce it correctly and try to ignore my mispronunciation. Exponential decay. So now I'm going to talk about what the exponential decay is. A situation in which a quantity is decreasing exponentially. This is the definition here. Now, what does it mean to decrease exponentially? Well, it means that the population or a quantity or whatever of something is decreased by the same factor after regular intervals. So after passing of the same time, for example 1 hour, the population or a quantity decreases by the same factor. I will give you examples shortly. So now, when does it occur? It occurs frequently in the world around us. For example, radioactive substances decay in this way, or the items that depreciate in value. Okay, so you may remember your first module this year about finance and about economy. So we talked about depreciation of assets or something that you have. Or another example of the decay, of the exponential decay, is the transient phenomena in electric circuits. You will encounter this in some of the exercises that follow. Okay, so let us start with the investigation. Radioactive decay. Consider a radioactive substance with original weight 20 grams. It decays by 5% each year. So it means that after each year the weight decreases by 5% because part of this substance decays to something else, and this something else is not taken into this weight. So what we measure is the weight of only the substance that we are interested in. For example, uranium-235 or something, but the numbers here would not fit uranium perhaps. So imagine a radioactive substance with these properties, which is unknown to us. We do not know what the name of this substance is. And what we have to do is to find the expression for the weight of the substance, W sub n, after n years. Okay, so to do that, I can write here. So imagine that W sub 0 is the weight of the substance after 0 years, so the initial weight of the substance. Now, after 1 year passes, you have this value decreased. Now it has to decrease by 5%. So what does it mean? Initially you had 100%. Then when you decrease it by 5%, you get 95%. So what factor corresponds to 95%? Of course, it's 0.95. So what you have to do to find the weight of the radioactive substance after 1 year is to multiply 20 by this factor of 0.95. Okay, so this is what you get. I will not evaluate the value because it's not so interesting, but what we need is to find a pattern. So let me continue. After 2 years, the weight of the substance, which was 20 times 0.95, is again decreased by 5%. So this here is multiplied again by 0.95. So this should be 0.95 times W sub 1, which is 0.95 times 0.95 times W sub 0. Okay, so it must be 0.95 squared times W sub 0. So this is what you get after 2 years. After 3 years, we have again 95% of what we had after 2 years. So the weight of the substance after 3 years from the beginning is 0.95 times the weight after 2 years. But since the weight after 2 years is expressed here, it should be 0.95 times 0.95 squared times W sub 0, and you see that this is nothing else than 0.95 to the power of 3 times W sub 0. So this is what you get after 3 years. Now we can easily generalize and write down what we should get after n years. So if after 2 years we had 0.95 to the power of 2 times W sub 0, after 1 year we had 0.95 to the power of 1 times W sub 0, which is 20, and after 3 years we had 0.95 to the power of 3 times W sub 0. So after n years we should have 0.95 to the power of n times W sub 0. So this is the formula that's going to be used for estimating the weight of the substance after n years. If we replace n by x, what we get is the weight as a function of x, which would be W sub 0, which is 20, times and 0.95 to the power of x. So this would be the exponential function, or the function corresponding to the exponential function, and it would describe the weight of this sample as a function of x, which is time this time. Okay, so this is part A. In part B, use a spreadsheet to calculate the weight of the substance after each of the first 20 years. So again, let me go to GeoGebra and try to use this formula and calculate the weight of the substance. So here is the GeoGebra again. Let me choose the spreadsheet view. Again, the first column will be devoted to the number of years, and here we should have the weight of the substance. The initial weight of the substance was, as far as I remember, it was 20 grams. So this is what we started with, and then each subsequent year we should have the following formula. We should have equals 20 times, and now 0.95 raised to the power of, and now the number of years, so it should be A2, like this. Okay, so now let me copy this down to 20. I hope it works this time. Does it? No, it doesn't, so let me do it again. Let me try to choose this and go to this, and once more. Oh, I will just replace it by 20. Okay, so I have the first 20 years, and now I have to copy down this formula like that. So this gives me the time sequence of the weights of this radioactive substance as it changed year after year for the first 20 years. Okay, so I had to do something with this, and now let me remind myself. In part B, I had to use a spreadsheet to calculate the weight of the substance after each of the first 20 years. So this is what I did. Now graph how the weight of the substance changes in time. So the last part to this is to take these values and graph them. So I have to create a list of points again. Now right click on this middle region and zoom to fit. So here we are. Here are the points. And finally, let me include also this function. So y equals, it was 20 as far as I remember, 20 times 0.95 to the power of x, like this. So this is the exponential decay of the radioactive substance. So you may see that it starts at 20 grams, and as time passes, its weight is reduced. It's reduced in such a way that after each year we get 95% of what we had the previous year. So you see it decreases, but it never approaches the zero value. It only asymptotically gets closer and closer to it. So you can see that this is a real exponential decay like that.